Good morning, happy Friday, happy weekend, whenever you're watching this. So today we are going to continue on with friction. We did address friction a little bit last class. You guys did the friction labs comparing the static friction to the kinetic friction and then calculating the coefficient of frictions, the different frictions at the end. So we are going to elaborate a little bit more on that and kind of talk about what is friction, how to calculate coefficient of frictions and all that. So we know that friction is believed to be caused by tiny bonds between two different surfaces. So if you have this picture on the top right corner here of the box sitting on the ground, and then it kind of gives you a close-up view of the two surfaces together. So we know that every surface, if you looked at it on the microscopic level, it has tiny little ridges and bumps. And depending on how deep those ridges are, how many, it's going to change your coefficient of friction. So it's going to make it harder or easier to slide objects across it. So in order to get an object moving, you have to overcome, or that force has to overcome the force that's holding them together. So if you have a really heavy box sitting on top of a rough surface, you have two characteristics that are going to make force greater, the force of friction greater. So here, if you're trying to start sliding a box like you saw in the lab last class, you should have seen that it takes more force to get something moving than it does to keep it moving. So that is something that we're going to talk about. So we're going to have our two different categories of friction. We have static friction, which is the force of friction when an object is not moving. That is always going to be greater than kinetic friction. So you saw that with the box. So when it was sitting still, the amount of force required to get that box moving was greater than the amount of force that was required to keep it moving. Some other examples of static friction other than the box sitting there could be parking your car at an incline. So we know that gravity is always pulling it down. That could be your it's not necessarily an applied force, but it is a force acting on that object that would make it roll down the hill. So without friction, the car would roll down the hill. But with friction, there's a great enough bond between the surface of the tire and the road that that car will not slide down the road. Another example here is this guy sitting on the desk. So he's like leaning up against the desk. And since he's still sitting there and not laying on the floor, that means that the force that he is applying is not great enough to overcome the force of friction between the legs of the desk and the floor. The other examples here we have are kinetic friction. So these are happening when the object is moving or in motion. So here we got a guy pushing a box across the floor. This is just what you guys did last class. Another example would be rubbing two objects together and that kind of thing. So friction, we know, always opposes applied force. So if we are pulling our block towards the left, we know that the friction will be going towards the right. So anytime you have an applied force, you're going to have an opposing force of friction. So the two frictions, we're going to have to differentiate between them. So we're going to have F of S is going to be a resistive force that keeps the object at rest. We know that it's going to be equal but opposite of your applied force. And then kinetic friction will be F of K, and that's going to be your resistive force once the object is in motion. It's always going to be less than static friction. So if you look at this graph on the right here, we have friction and applied force. So you can see that this is very similar, or should be very similar to the results you guys got in your in your lab last class. We also know that the force of friction is going to be proportional to the normal force. So you guys did a little bit of this in the lab. You were calculating the coefficient of friction, which is right here on the right-hand side. So this little symbol is called a mu, just like a Pokemon. So it's a mu. This stands for coefficient of friction. This is, generally speaking, this doesn't have a subscript of S or K, so we don't know if you're specifying about static or kinetic friction, but in general, the coefficient of friction will always be the force of friction divided by the normal force. So here we should have been able to calculate that last class based off of the peak of your pulling your object versus the force that was required to keep it moving. So friction can be calculated approximately, and it's usually based upon the weight of the object and different surface characteristics. So here we have two examples of that. If you have a smaller contact area between the two pieces, or a different type of surface. So here we have quite deep ridges and things, and the actual surface that touches is very low. It's a low amount of surface. And then on this side, on the right side, we have a larger contact area. So these pieces kind of fit together better almost, and you have more contact there. So friction will be higher when you have larger amounts of surface contact, so you can have like a rougher surface. And weight also increases that. So you can see that here if you compare the magnitude of the two sets of arrows. So the arrows on the right are greater, so they have a greater magnitude than the arrows on the left. So that means that you have more force and a rougher surface. So you would have a higher coefficient of friction there. So the coefficient of friction, these are just a bunch of examples. So all the coefficient of friction is, it does not have a unit, so it's just a number value, and it's usually between 0 and 1. It can be a little bit over 1, but it's usually between 0 and 1. The higher the coefficient of friction indicates that it's going to take more force to overcome it. So if you look at some combinations here with a pretty high friction, coefficient of friction would be like between rubber and concrete. So if you look at that one, it's the fourth one down between rubber and concrete. A really high coefficient of friction for both static and kinetic friction. So all that means is that you're going to have to apply a lot of force to that object to get it moving and keep it moving, compared to something with a lower coefficient of friction like steel on ice. Okay, so you can imagine the differences in those surfaces that could cause those things. Also will make a big difference on how heavy the objects are. So when you start comparing the two surfaces, the coefficient of friction will be the same between any of these surfaces. So if you have steel and copper, the coefficient of friction should be about those values no matter how much or how little you have, because the surfaces of them are pretty standard no matter what the sample size is. So an example of these, first one's going to be overcoming static friction. So a pack of dogs are pulling a wooden sled and rider of combined mass of 238 kilograms across dry snow. So how much force do the dogs need to apply to cause the sled to begin to move? So here we have our free body diagram. We have the circle that represents the person on the sled. Their total mass of the sled and the person is going to be 238 kilograms. So from that, we have his mass, and we are assuming he's on Earth. We can then calculate the force of gravity. So at the bottom there, it says Fg equals mg. So the force of gravity will just be the mass of the object times gravity. So we find out that our force of gravity is going to be 2,332.4 newtons down. So we know that the normal force will be equal but opposite to that. So your normal force is going to be 2,332.4 newtons up. Then we know we have applied force coming from the dogs pulling the sled, and then we have the force of friction balancing that back out. So we need to figure out how much force the dogs need to apply to cause that sled to move. So what we need to figure out is the force of friction needed to overcome that. So what we have here in this formula is force of friction equal to the coefficient of static friction times the normal force. So in this case, we know what our two surfaces are. So we know that we have a wooden sled and we have dry snow. So we would then be able to look on our chart and see that the coefficient of friction is 0.22. So you are substituting those values into this simple formula to solve for the missing variable. So we know that the normal force is 2,332.4 newtons up. We know that the coefficient of friction, of static friction for these two surfaces is going to be 0.22. We'll multiply those to solve the force of friction. So what we get is that the force applied has to be greater than 513.13 newtons, or that sled will not move. Another example is talking about kinetic friction. So you push your 27 kilogram wooden desk across the wood floor with a constant velocity. Find the force of friction and the applied force. So we're looking kind of at two things here. So we know we have wood on wood. We'll be able to look up that coefficient of friction and use that in our problem. So over here on the left-hand side, we have a free body diagram. The desk is represented in the circle as our object. It is 27 kilograms. So the first thing we want to figure out, our force of gravity. We also want to figure out the normal force because we know we're going to need that. So we're going to figure out the force of gravity on that object. So we have 27 kilograms times acceleration due to gravity, which is 9.8. So we get a force of gravity of 264.6 newtons down. We know that the normal force will be equal but opposite. So normal force is 264.6 newtons upward. And now we know we have an applied force and a frictional force. So in this case, it says that it's moving at a constant velocity. So that's our indication that acceleration is 0. Okay, so that we know if it's moving at a constant velocity, it's not speeding up or slowing down, it's just continuing at the same speed. So acceleration will be 0 in this case. So in this case, since that's 0, your force of gravity is going to be equal to your normal force, and the applied force is going to be equal to the frictional force because we have a balanced set of forces. So we can use our coefficient of friction formula to solve for the force that we need to apply. So same thing as the last one, we're going to figure out what the coefficient of friction is between wood and wood, which is 0.20. That comes from the chart. And then we're going to multiply that with the normal force that we calculated of 264.6. So we get the force of friction as 52.92 newtons. So that means the applied force has to be equal but opposite of that. So our applied force is going to be the 52.92 newtons towards the right, and the force of friction will be opposite of that at 52.92 newtons to the left. And that's it. So that's the end for today. You guys have just a couple of practice problems to work on today. If you need time to finish up your lab, feel free to do that. The equipment is actually still out on the table. So if you are in class and you want to go back there and finish anything up, you're welcome to do so. It has been edited since last class. So if you get back in and you want to see what's been edited on that, it might help you out. It's not going to change anything. I only assigned a couple of questions for you guys for that analysis. So if you're done, have it turned in, that's great. But if you want to get that equipment back out and do some more of this lab, you can. Otherwise, you guys just have your assignment to do, and I will see you guys on Tuesday. Actually, I won't see you guys on Tuesday. So next class, again, we'll have to do this because I have a meeting in the afternoon. Forgot about that. So all right, so that is it. You guys have just a couple of practice problems to get done that go along with friction. I reset the due dates for that, so it's not due like today. So I'll get in there and reset that for you, and then make sure that you have your labs completed from last class and turned in. Like I said in my announcement, I'm not actually going to be addressing anything this weekend, so just make sure everything's in there. If you have any really pressing questions, you go ahead and send them to me, but I won't be replying to anything until Monday. So if you do have questions, feel free to stop by, but I think you guys will be good on this. This topic's not extremely difficult. So just make sure you get that assignment done, get your lab turned in, and I will see you guys next week.